So now you see the screen in front of us. All we did was worked on the left-hand side of the equation. We rewrote that sine squared theta in terms of 1 minus cosine squared theta. Ended up distributing that 3. And that gave us what we wanted when we combined like terms. It gave us that right-hand side of the equation. So we're done with that proof. Okay, so you see another identity in front of us that we want to show is true. Cosine parentheses x minus 90 degrees minus cosine parentheses x plus 90 degrees. And we want to show that that's equal to 2 sine x. Okay, so I see a difference and a sum of 2 angles for cosine. So I'm going to use the sum and difference of angles for cosine to rewrite those first 2 terms on the left-hand side. And I'm going to work on the left-hand side only and make it look like the right-hand side. So the formula for cosine of a difference of angles was cosine of the first angle, x, cosine of the second angle, in this case would be 90 degrees, opposite sign that was in between, so plus, sine of the first, which is x, sine of the second, which is 90 degrees. So that was just this first term. It would be wrong if you thought of that cosine as being able to distribute to x minus 90 degrees, because that is our argument, and cosine is a function. We can't do that. So now I'm going to look at cosine x plus 90 degrees. Again, I'm going to look at the sum of 2 angles for cosine. We have to be careful because of this negative sign out here. So I'm going to put parentheses around this whole thing when I rewrite it. Okay, so cosine of a sum of angles, it's almost the same thing as a difference. So it's cosine of the first x, cosine of the second, 90 degrees. Opposite sign that's in between, so this one would be minus sine of the first x, sine of the second, 90 degrees. Okay, so I noticed that I can evaluate cosine of 90 degrees, sine of 90 degrees, again, that cosine of 90 and sine of 90. So at 90 degrees, so if you're looking at the unit circle, 90 degrees is getting us up to this positive y-axis. So remember on the unit circle, your x values are cosine of that angle and your y values are sine of that angle. Well, if I'm looking at the x value here, when I'm at the positive y-axis, my x value is 0, and my y value here is going to be 1. So I'm going to go in, wherever I see cosine of 90, I'm going to replace it with 0, and sine of 90, I'm going to replace it with 1. So doing this, I would get cosine x, all times 1, which I really don't need there, plus sine x, and I just said that cosine of 90 was 0, so that should be 0. And I need to put that there. Sine of 90 is 1. I'm going to distribute this negative as I rewrite it. So this is minus cosine of x times cosine of 90, but cosine of 90 again is 0. Distributing my negatives, so minus times a minus is actually a plus. So this is sine of x times sine of 90, but sine of 90 degrees is 1. So anything times 0 is 0. So we get this sine x plus sine x. Those are like terms, so adding the coefficients in front. So 1 plus 1 is 2. So this is 2 sine x. This is exactly what we wanted to show. So we are done with that proof. So the next question, we have 2 triangles in front of us. We want to figure out what B, C, and D are given that A is 5. So I know right here, A is 5. I have the angle 60 degrees. That A value, that side, is the adjacent side. So I have the adjacent side, and I know this angle. If I was going to figure out what C is the hypotenuse. So I kind of think about which trig functions use adjacent and hypotenuse, and that is cosine. So cosine of the angle 60 degrees is equal to the adjacent side of that angle 60 degrees, which we were given as 5, all over the hypotenuse, which in this case is side C. Cosine of 60 degrees, if you want to use your hand, cosine, remember you count downwards, so this is 1 root 1 over 2, so that's 1/2. So 1/2 is equal to 5 over C. We can think of this as clearing the fraction, getting rid of the denominator. Looking at both of these fractions, our least common denominator is 2C. So let's just multiply 2C on both sides of our equation so we can get rid of the fraction. Well, 2 goes into 2C, C times.
How did you get 1.5? Sorry.
Yeah, that is, I evaluated cosine of 60 degrees.
Oh, okay.
So if you wanted to use the hand like we were teaching in class, so we have 0, 30, 45, 60, and 90. Cosine starts at top, sine on the bottom. So
Okay.
the formula is root n over 2. And n is the number of fingers that we're going. So counting how many fingers down to 60 degrees, that's just, and starting at this top one we're not counting is 1. So root
Okay.
1 is 1 all over 2. So that's how we got the 1/2. Over here on the other side of the equal sign, we wanted to cancel our C's. That's why we multiply by the LCD. So we're left with 2 times 5, which is 10. So we now know what C is. There's a couple of different ways that we could figure out what B is. We can use a ratio sides using a trig function, or it's a right triangle, so we can use Pythagorean theorem. So we know that 5 squared plus b squared is equal to the hypotenuse, which is 10 squared. So I have 25 plus b squared equals 100. Subtracting 25 on both sides, so b squared is 75. So I know my b value is the square root of 75. I would probably pull out the biggest factor that is a perfect square from 75. 75 could be rewritten as 25 times 3. So b is equal to, well, square root of 25 is 5. And then we're going to leave the 3 under the radical. So now we know what b is, and we know what c is. Let's go to the triangle on the right-hand side. Well, this is a 45-degree angle. So now we have the hypotenuse, and we know that this angle is 45 degrees. I probably wouldn't use that. Knowing that that's 45 and this is 45, I know that D and E have to be the same value. So if I knew that, if I knew D is equal to E, then when I rewrote this, like D squared plus E squared equals C squared, well, I can say, well, D is the same thing as E, so E squared plus E squared equals C squared. Or 2e squared equals c squared, but we're given c, so let's just replace that with 10. So 10 squared. So 2e squared equals 100. Divide both sides by 2. I get e squared equals, again, 50. Divide both sides by 2. So e is equal to the square root of 50, which is square root of 25 times 2. Under the radical, and now if we look at the square root of 25, that's 5 root 2. So E is that, but D is equal to E, so D is also equal to 5 square roots of 2. Let's just say you didn't see that, and if you didn't see that, that's okay. If you use this 45-degree angle and you knew the hypotenuse, kind of think about which trig functions use hypotenuse. We can look either at the adjacent or the opposite sign. side, which means we could use sine or cosine there. So let me just do cosine. So if I had cosine of 45 degrees, which is the angle we know on the second triangle, we know that this is equal to the adjacent side of this 45, which in this case I have is D, all over the hypotenuse, which we found before was 10. Square root of 45, so counting down to 45 degrees, which is my middle finger, so that's 1, 2. So that's square root 2 over 2 equals D over 10. If I multiply both sides of the equation by the least common denominator of 2 and 10, which is 10, this would give me 2 goes into 10 5 times. So this is 5 root 2 is equal to D, which is what we said down here. So then you could either use a Pythagorean theorem, or you could say, if you didn't notice again that they're the same values, we can say, oh, well, if I use sine of 45 degrees, this is equal to the opposite E all over the hypotenuse 10. Sine starts at the bottom and you count up to the number of the degree. So counting up, I have root 2. So root 2 over 2, just like the other one was, is equal to E over 10. So if we multiply both sides by 10 again, we'll get 5 root 2 is equal to E. So there's a couple different ways that you could have approached that to figure out what the sides of those triangles were.
Okay, I got it.
Okay, so in front of us is another example. F of x is equal to cosine of the argument 1/2 x minus pi, and that parentheses, and then plus 1. So we want to graph this. Normally, cosine without any shifts or stretches is between 0 and 2 pi. So what I would do is I would take my argument of cosine, or if it was sine, I'd do the same thing, and I would sandwich it in between what a normal period is, which it starts repeating itself every 2 pi.
Mhm.
So we have 0 is less than or equal to 1/2 x minus pi is less than or equal to 2 pi. So our goal in here is to get this x by itself. So let's add pi to all sides of our equation. So we get pi is less than or equal to 1/2 x is less than or equal to, well, 2 pi plus 1 pi is 3 pi. So now I want to get x by itself. I don't want 1/2 times x. So I can either divide all sides by 1/2, or easier to think of it as multiplying everything through by 2. So 2 times pi, 2 pi, is less than or equal to, well, when we distribute 2 in between the inequalities, that will cancel with that 1/2, just leaving us with x, is less than or equal to, and 2 times 3 pi, that's 6 pi. So the length in there, we're starting at a 2 pi for one period and ending at a 6 pi. So always do the end of a period, which is 6 pi, minus the start of that same period, which in this case is 2 pi. This would give us a length of 4 pi. So I know my period, it's going to repeat itself every 4 pi. Okay, so that's going to help me. Also, these two values that we got while we were getting x by itself. So let that be our start. So I'm going to start at 2 pi. I know that the end value over here, it's going to end at 6 pi. So I want to figure out what is the halfway mark between the start and the end. So sometimes they're easy to see, sometimes they're not. If you can't see it, you're going to take your start value, 2 pi, plus your end value, 6 pi. And you're going to divide that by 2, or think of it as multiplying by 1/2. So 1/2 times 2 plus 6, so that's 8 pi. So this is equal to 4 pi. So I know that the halfway mark in between that period is 4 pi. Quarter mark, so halfway between 2 pi and 4 pi, I can see is 3 pi. But if I sum those, 4 plus 2 is 6. 6 divided by 2 is 3. So this is 3 pi. 3/4 mark of one period. So I would look at the halfway mark and my end-way mark, trying to find the halfway point. I can see that's 5 pi, but again, if you can't see it, 4 plus 6 is 10. 10 divided by 2 is 5, so this would be 5 pi. Okay, that's going to make it so much easier to graph this, that we have the start and end of one period. So let me just write that on the graph. Okay, so I'm going to just do 2 pi, 2. I probably should make them a little bit further apart. Let's do that. Okay, so we have 2 pi here, 3, 4, 5, 6 pi. So normally, and I'm just making sure that I wrote this down right, and that was it, amplitude was 1, but I'm trying to find my mouse. Too many screens. Yeah, that's right. Okay, so my amplitude was 1 here. There's no number shown. So that means normally I would have a max of 1 and a min of -1. The problem is that I have this +1 outside, so this is a vertical shift up 1. So now my max is not at 1. If I shift that up, my max is now at 2. And my min was at -1, but if I shift that up 1, it's now at 0. So I'm going to treat this y equals 1, this horizontal line, as if it was my x-axis when I'm graphing this. So I think about cosine. Cosine at 0 degrees is 1, so it's at the max, but we shifted it up 1. So cosine at 2 pi, the starting value is going to be at 2. My quarter mark, you're going to hit your midway line. So I'm going to hit this value at 1 at 3 pi. At 4 pi, we're going to hit our minimum, which ends up being 0. At 5 pi, we're back up to the midway line. And at 6 pi, I'm back up to the max. And so I have this graph that looks like this. And it's going to start repeating itself. It wants to know the domain, the range. Well, domain, we don't have any problems. Only ones that we're going to have problems with domain are trig functions that have a trig function in the denominator. So cosine, sine, all real numbers. The other ones we have to be worried about. So our domain here are all real numbers. So -infinity to infinity. The range are all the y values you're hitting on the graph. So the range in this case, because of the shift, our smallest y value we hit is 0 with a bracket, and the largest y value that we're hitting on here is 2. So that is our range. Our phase shift is the start value. So we are not starting at 0, we're starting at 2 pi. So our phase shift is 2 pi, I can say to the PS for phase shift, is equal to 2 pi to the right. Or you could have just said -2 pi. I tend to just say what way we're going, so 2 pi to the right. The next part of this question asked you to graph the reciprocal function. So our reciprocal function was the secant of 1/2 x minus pi plus 1. Well, to get this graph, we had to graph the cosine function, which we have. Anywhere it hits our midway line, those are our vertical asymptotes. It's undefined there. So I can see that it's hitting there at 3 pi. That was a 5 pi. It's going to hit again at 7 pi. We'll come back and look at the domain of the reciprocal function. So the shape of secant are like kind of like parabola shapes going off of the max and the min. So here we would have this parabola shape. Right here we'd have this parabola shape facing down off the min, max, parabola shape facing up. So that was the graph of the reciprocal function. It called it g of x. I called it y, so g. It wanted to know the domain. So the domain, we have to exclude any vertical asymptotes. And again, I could see a pattern here. I'm also going to hit one at here. So 1 pi, I can notice that it's every odd number, 1, 3, 5, 7. So to write odd numbers, that's like 2 times x plus 1. Or maybe let's do, because we have x using it on other things, maybe n. So 2 times n plus 1 is an odd number. So our variable x cannot equal 2n plus 1, where n is equal to an integer. So integers are the numbers like negative infinity, dot, 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 negative 3, negative 2, negative 1, 0, 1, dot, dot, dot. So that's our domain of the reciprocal function. The range of our reciprocal function, like looking at the blue graph, we're hitting all the values from negative infinity until we hit 0. So I have negative infinity to 0, including, because we do hit that number, union. So I have a gap between 0 and 2. So I don't have any y values for the reciprocal function there. And so that's going to be from 2 to infinity. So that would be the range of the reciprocal function. Okay, so I have f of x is equal to x cubed plus x squared minus 8x minus 12. We want to find all the zeros of this polynomial. So we had learned some rules to help us find zeros. And there's what is called the rational zero theorem. So we're wanting to find p divided by q. P are always factors of your constant, so numbers that go evenly into that number. So I'm thinking of numbers that go evenly into 12. They can always be positive or negative, but 1 always goes into a number evenly. 12, 2 also goes in there. 3 goes into 12 evenly. 4, 6, and 12. Q are always the factors of the leading coefficient. So our leading coefficient in this case, there's none, you can't see it, it's 1. So only numbers that go in there evenly are plus or minus 1. So if I look at every number in P and divide it by 1, I'm going to get the same thing as P itself. So the only possible rational zeros, and it has to be rational for this to work, are 1, 2, 3, 4, 6, and 12. And so now I would just start using my synthetic division, hoping that I would get a 0 in that last row. And then that would tell me that that was a 0 with a polynomial.
Okay.
Should we go through it?
Yeah, sure.
Okay, so let's write down the coefficients in front of our variables. If you had a missing power, for instance, let's say that x squared was not in that polynomial, we'd have to put a placeholder. We'd have to put a 0 there. But I can see in descending order of powers, I'm not missing any of those exponents. So I'm just going to write my coefficients, 1, 1, -8, and the constant -12. You always bring down the first number. So in this case, it's 1. Multiply it by the number that we're seeing if it goes in evenly. So in this case is 1. So 1 times 1 is 1. Always sum your columns. So 1 plus 1 is 2. So that's going to be the bottom row. 1 times 2, okay, that's 2. Put it underneath the next number, sum it. -8 plus 2 is -6. 1 times -6 is -6. So I can see that this is not 0. So it does not go in there evenly, which means it's not a 0 of that polynomial. So then I just go down to my next number 2. Again, writing the same coefficients, 1, 1, -8, -12. So bringing down the first number 1, 2 times 1 is 2, 1 plus 2 is 3, 2 times 3 is 6, -8 plus 6 is -2, this is -4, it's not going to work. So now I go to 3, 1, 1, -8, -12. Bring down the first number 1. 3 times 1 is 3, 1 plus 3 is 4, 3 times 4 is 12, -8 plus 12 is 4. 3 times 4 is 12. And I'm happy because I got a 0 there. So this tells me x equals 3 is a 0. The next part of the question is wanting us to rewrite this as a product of factors. So my factor is just subtract 3 on both sides. X minus 3 is the factor. Recall the bottom row, once we find our 0, it's 1 degree less than what this top row was. This top row was a cube. So this was degree 3. So this down here has to be 1 degree less. So this is degree 2. So this would be 1x squared plus 4x plus 4. So since that's quadratic, I don't have to go through and continue to trying to find the zeros by plugging in the numbers I found for P over Q. I could just factor this bottom row, 2 numbers that multiply to 4, but also sum to 4 would be 2 and 2. So x plus 2 times x plus 2. Looking at when that equals 0, that's when x is -2. So we have a 0 of x equals -2. Multiplicity is 2. And x was equal to 3 was also a 0 of that polynomial. And then part B wanted us to rewrite this as a product of linear and or quadratic, if the quadratic was irreducible. Ours was reducible. If it had imaginary numbers, when you were trying to find the zeros, then keep it in that quadratic form. But we could rewrite that polynomial f of x that we were given. This is the same thing as x minus 3 times x plus 2 times x plus 2. If you wanted, you could rewrite that as x plus 2 quantity squared. Okay, so we found the zeros of that polynomial. So that's telling us where it's going to be crossing or touching the x-axis if we had to go through and graph that. Okay, so we're looking at solving some trigonometric equations. We have the first one, sine x plus sine 2x equals 0. We want to manipulate this so that they're both sine x, not sine 2x. I noticed that this is a double angle, and there is some formulas to rewrite our double angle. I have to think about it. I know that that's the same thing as sine of x plus x. So I know sine 2x is the same thing as, ends up being 2 sine x cosine x. So let's rewrite sine of 2x using this identity as 2 sine x cosine x. So doing that, we have sine x plus 2 sine x cosine x equals 0. And so now I see that I can factor here. There's two things in common, and it's set equal to 0. So let's factor out sine x. So if I factored out sine x, I would get 1 for the first term plus 2 cosine x for the second term is equal to 0. So I'm looking at when is sine x equal to 0? And when is 1 plus 2 cosine x equal to 0? Well, sine on the unit circle is our y value. So you're looking at the unit circle and you're kind of thinking about when is y 0? Well, y is 0 here at 0 degrees, at pi, 2 pi, 3 pi. So in this case, but we only want it between 0 and 2 pi. So for the first equation, this is when x is 0 and pi. The second equation, it's linear, so I want to isolate my trig function. So I would subtract 1 on both sides, and I would get 2 cosine x equals -1. Divide both sides by 2, I get cosine x is equal to -1/2. So I would ignore the negative for a moment. I'm just thinking about the first quadrant. What value of cosine would get me back +1/2? And that's when x is 60 degrees, or in radian measure, that would be pi thirds. The thing is, that would give me back +1/2. So I have to think about when is cosine negative? Well, cosine, again, is the x value on the unit circle. X is negative in the second quadrant and in this third quadrant. So I know my reference angle is pi thirds. So pi thirds here, I could get that by taking pi minus pi thirds. Common denominator, 3 pi thirds minus 1 pi thirds. So this would be when x was 2 pi thirds. So I'm going to just change that to 2 pi thirds. And then it's going to be over here in the third quadrant. My reference angle again is pi thirds. So if I add pi thirds to pi, getting a common denominator, 3 pi thirds plus 1 pi thirds, that would be at 4 pi thirds. Those are the only values that we have between 0 and 2 pi. And so those would be the solutions to that first equation. Second equation, let's go back and let's look at this. I don't know what, it's because this 4 theta is here. So that's kind of screwing things up. If that had been theta, we would just solve for sine. But we can say, okay, let some value, let's say a equal 4 theta. So now I'm really solving this equation right now for 2 sine a is equal to square root of 3, root 3. So if we divide both sides by 2, we get sine a is equal to root 3 over 2. So I'm kind of working backwards, thinking to myself, what angle of sine would give me back root 3 over 2? Well, that's at 60 degrees or pi thirds. So this is when a is equal to pi thirds. We have to add in this plus 2 pi k for now. Or sine is also positive in the second quadrant. So thinking about pi thirds again in the second quadrant, so 3 pi thirds minus 1 pi thirds, 2 pi thirds. So a is also equal to 2 pi thirds plus 2 pi k. But I don't want A, I want to know what theta is. So let's go back up here and let's rewrite this. A as 4 theta. So we have 4 theta is equal to pi thirds plus 2 pi k. So again, 4 theta is equal to this. We want theta by itself. We don't want 4 in front of that theta. So we can think of that as multiplying both sides by 1/4 to get theta by itself. Okay, so that gives me theta is equal to, distributing here, we have pi 12ths plus distributing here, this would give me 2 pi k over 4. I could reduce, but I actually really want to write that as a single fraction, so I'm not going to reduce any. Again, multiplying both sides of the equation by 1/4, we get theta is equal to 2 pi 12ths plus 2 pi k over 4. Okay, getting a common denominator first will make your life a little easier when you choose values for k. I notice the smallest number that 12 and 4 go into is 12. So multiplying that second fraction on each of those thetas by 3/3 will get us 12 in the denominator. So theta is equal to pi plus 6 pi k all over 12. And in this case, theta is equal to 2 pi plus 6 pi k all over 12. So we're going to look at when k is 0, and we're going to keep on raising that up one integer until we're no longer in between 0 and 2 pi. So if I plug in 0 for k, that would just give me pi 12ths for that first theta. And 2 pi over 12, or pi 6. 2 pi 12ths is pi 6. Those are both between 0 and 2 pi, so we're still good. Now I'm going to plug in k equals 1. So k equals 1. 1 times 6 pi is 6 pi. 6 pi plus 1 pi, so this is 7 pi 12ths. Plugging in 1 for k here, so that's 6 pi plus 2 pi. That's 8 pi 12ths. I'm just going to reduce it. 4 goes into both of those, so that's 2 pi thirds, which is still between 0 and 2 pi. So now looking at when k is 2. So plugging in 2 for k, I got 2 times 6 pi is 12 pi. 12 pi plus 1 pi is 13 pi over my denominator of 12. Again, plugging in 2 for k on the other equation. So we have 2 times 6 is 12 plus 2, that's 14 pi over 12. Both divisible by 2, so this would be 7 pi 6. Now I need k equals 3. So 3 times 6 is 18, 18 plus 1, so that's 19 pi over 12. Plugging in 3 here, so 3 times 6, so that's 18 pi plus 2 pi, so that's 20 pi 12ths. Both divisible by 4, so that's 5 pi thirds. Next time I plug in a number, we should get things bigger than 2 pi, but let me just show it. So if we did k equals 4, 4 times 6 is 24, 24 plus 1, that's 25 pi 12ths. Well, 12 goes into 25 more than twice, so that's bigger than 2 pi. So that's outside of between 0 and 2 pi. Same thing if I plug it into the second equation. 4 times 6, so that's 24 pi plus 2 pi, that's 26 pi 12ths. Again, that is too big. So we're done. And we have all these values. So 8 solutions between 0 and 2 pi for that second equation.
quotient stuff.
Yay.